Explanation of the calculations for the Precipitate Lab. Please disregard these boxes over here until I bring them in and use them. So here's the equation for the reaction. And I think that by now what all of you know is that the sodium carbonate, as we set it up, the sodium carbonate was the limiting reactant. Calcium chloride was the excess. So I've got some numbers here to use. They're not going to resemble the numbers you have. I've intentionally made them different. Let's say that you started with 3.15 grams of the limiting reactant, sodium carbonate. And you did the first step of the calculations, which is that you determined how much of the product we should make based on 3.15 grams. And let's say you came up with 3 grams. So the math tells you that if you start up with this much, you're going to end up with this much product. And then let's say you, the next day, did your weighed it and found that this was your actual. Okay, so this is your actual, and this is the expected mass. And that's great. And then you did your percent yield calculation, and it gave you that you had a 92% yield, which in turn means an 8% loss. Okay, so this is pretty much standard. I have found that most students are really clear on this part through here. Beyond here, this is where it gets confusing. So in the instructions that I've given to my students, what I said was the next step is to figure out how much of each of the reactants was actually used. Now, that question was phrased in an intentionally vague way because the truth is you don't have to do any math to find out how much of the sodium carbonate was used. 3.15 grams of it was used. We know this because it is the limiting reactant. And by definition, the limiting reactant is the one for which all the stuff you put in gets used. There's none left over. The question is how much of this was used. Before I go on to that, some of you might say, well, I understand that that much would be used if we had made 3 grams, but we didn't actually make 3 grams. We made 2.76. So shouldn't I go back and recalculate it based on that? Okay, no, you shouldn't, because we truly used 3.15 grams. However, the answer didn't go to this. It actually went, and that's loss. And that's something we have to deal with later. But it doesn't mean that we didn't use 3.15 grams. It just means that along the way, some was lost. But now we have to figure out how much of the other reactant was made, was used. And again, you might say, well, which number should I base that on? It's a stoichiometry calculation, but should I base it on which of these? Okay. The answer is that you should base it on the mathematical ones, not on the actual one, okay? Really, the significance of the actual one does not apply to determining the amount of the excess reagent used, okay? So you should base it on either 3.15 grams of sodium carbonate or your expected mass of the product. Both of those will give you the exact same answer. And so let's say that stoichiometrically, determined by the math, you get that 3.02 grams of calcium chloride should be used. I didn't calculate that number. I have no idea if it's right, but whatever. It does the job in this spot. All right. Now you've got 2 different scenarios. You've got 2 different ways of thinking about it. One is if you take 3.15 grams of sodium carbonate and you combine it with 3.02 grams of calcium chloride, you expect to get 3 grams, but there might be some loss. Or you can think if you use 3.15 grams of this and 3.02 grams of this, what you're actually going to get is this 2.76 because there is loss. Now, the next step, the completion of the calculations, could use either of these numbers, but they need different treatments. So let's deal with the expected value, okay? So let's say you're like, okay, I'm going to go with what the math said should have happened. And you're like, well, okay, I'm going to talk about 3 grams, 3.00 grams expected. Only I don't want to think about 3.00 grams. I want to think about 2,500 kilograms. And you have to pay attention. One thing that you can't lose is that this is not just 3 to 25. This is actually 3 to 25 million, or sorry, 25, what is it, 200, whatever it is. It's this times 1,000 because of the gram-kilogram transfer. So if you do that and you go, all right, we're going to just move this stuff out of the way for a moment. Get this out of the way for a moment. Okay, and you're like, okay, I just want to think about how many times, what number would I have to multiply 3 grams by to get 2,500 kilograms? Okay, and I call that number the multiplier. Okay, so if 3 grams times some very big number gives us 2,500 kilograms. What you could do is, so you have to divide 2,500 kilograms, converted to grams, by 3 to get the multiplier. The multiplier then goes over here. Oh my goodness. Okay, and these values also get multiplied by the multiplier so that you're scaling your amounts of each reactant by the same amount that the product is, and you get these really big numbers down here. Okay, you say like, okay, I'm going to figure out how many times you multiply this to go into, how many times does this go into this? And then I'm going to take that amount of times and scale this up by that number and this up by that number, and I'm going to end up with 2 really big numbers of grams. Only that's not your final answer, because it's just as it is not true that this amount of this plus this amount of this did not actually make this amount of this, then the scaled up of the sodium carbonate and the scaled up of the calcium chloride will not actually make 2,500 kilograms. It will make less. So what you need to do is then use that 8% loss to add an additional amount of each of the ones on so that you are overshooting in order to accommodate the loss and end up at 2,500 kilograms. So once you get that, then you know how many grams of each it is, and then it becomes a fairly simple calculation of just finding like dollar amounts per a certain amount of the reactants and doing that. And I don't find that students have a lot of trouble with that. It's figuring out the gram amounts of the reactants that's hard. So that's one way to do it. And if you want to do it that way, then feel free to just stop this video and go back and listen to me say that a bunch of more times. There is another way to do it, which gives you the same answers, which is that you actually base the entire ramping up thing not on your expected mass, but on your actual mass, like that. And you can see that the multiplier to get you from 2.76 to 2,500 is going to be a larger number than the multiplier that takes you from 3 to 2,500, because 2.76 is a smaller number. So the multiplier in this case would end up a slightly larger number because you're basing it on actual. Then the reason it's larger is that is inherently accommodating the loss. Because if you say that because you're starting from a smaller place to get to this, you're going to have a bigger multiplier. Therefore, that multiplier will work for this, and now you are inherently anticipating the loss, so you don't have to scale it up by that additional 8%. You just say, if I start on the assumption that this many grams of this plus this many grams of this will actually make a smaller amount, then all you have to do is scale it up to 2,500 kilograms and use that multiply on this, and that will give you the actual gram amounts of the reactants without having to add on an additional 8%, because the 8% is baked into this number. I hope that is useful, and as always, you may ask me further questions.